Okay. How many, what the freak is this dude's name? Hafþór Björnsson. How many of you know who Hafþór Björnsson is? You know?
Yeah, I think it's a different person, though.
Okay.
Do you watch Game of Thrones?
That's him!
Oh, yeah?
That's freaking dude. Yes, dude. Talking about the Mountain.
Sick.
Sandor Clegane, dude, is the Mountain on Game of Thrones. Do you guys, okay, I didn't know who Hafþór Björnsson was, but of course I know who the Mountain is. Right? Do you guys know who Sandor Clegane is on Game of Thrones? Oh, sick. All right. So, for those of you who don't watch Game of Thrones, what are you doing with your life? And you should watch it. And the Mountain is one of the characters in it. He's huge. He's a total badass. He was just in the news, actually. So I just heard about this yesterday. Was the actor that plays Sandor Clegane on Game of Thrones, which, by the way, I read all the books before the series even came out. Just FYI. So I did. So the actor, I'm just going to call him Sandor, okay, because his real name's too hard. Or the Mountain. I'll just call him the Mountain. So the actor that plays the Mountain was just in the news because he just won the World's Strongest Man competition. Dude is 6 feet 9 inches tall. He weighs 400 pounds. And he just won the World's Strongman competition by, among other things, he lifted up a barbell with, guess how many pounds? Over 1,000, okay? Like 1,040 or something like that. He could lift this whole front row, like no problem. Yeah, easily. You could lift 1, 2, 3, 4, 5, U6. Probably lift some cars. Like, it's crazy. And to think the dude is 6'9", and he had to lift it all the way from the ground up to, 6 feet 9 inches in the air. I thought, man, like, that's got to be a lot of work. Work. I started thinking about work. Yeah. That's a math concept. Well, it's a physics concept. And it has a mathematical definition, which I haven't really talked about in this class. I skipped the section on work and energy, but I wasn't happy about it. Like, if I had all the time in the world, I would have included that section definitely in this class because it's important, especially for engineers and physicists. So let me at least, be able to say that I told you guys about it. So the most basic definition of work, and by the way, work is work and energy. Let's start with that. What's the difference between work and energy? So yeah, I'm talking about the rigorous physical definition, the physics definition of the word work. We don't mean like, having a job that you go to all day. We're talking about in physics or thermodynamics, when they use the word work, they are referring to expenditure of energy, okay? So it requires energy to do work. Work and energy have the same units. They're basically the same thing. So right, there's multiple different types of energy, right? There's like thermal energy, there's kinetic energy, there's electrical energy, there's potential energy. And work is one of the forms of energy. It's what happens when you physically push something or pull something. Every object that is in motion or is accelerated is having work done on it or is doing work on something else. So the formula for work, the most basic formula for work, let's call it W, is its force times distance. So This is the applied force. This is the, or actually, let's say displacement. So naturally, I asked the question was, how much work did the mountain do in picking up this barbell? So let's just say it was 1,000 pounds. And he's 6'9", and he lifted it up to his head, 6 feet 9 inches, which is the same as 6.75 feet. So according to the formula, he did, so the force, by the way, the number of pounds that something weighs, that's a force. Right? Pounds, a lot of people confuse your weight with your mass. Your pounds is your weight, which refers to the force that you're being pulled to the floor with. So if you go to the moon, right, you won't weigh the same number of pounds, even though your mass will be the same. So this is a 1,000-pound force. And so he did 1,000 pounds of force over a 6.75 foot distance, expending 6,750 foot-pounds of energy. Okay. Fine. That's a ridiculous amount. Like, I'm probably not going to do that in the gym all week. If I went to the gym. So now I want to change the question up a little bit and imagine, so like the mountain is pretty tall. He's 6'9". He's 6 feet 9 inches tall. Let's imagine that he was 4,000 miles tall instead. That's my next question. Any idea why I chose that number?
Is that an actual mountain?
So Mount Everest is like 7 miles tall.
It's Mount Olympus on Mars, correct?
I don't know. I don't think it's. It's way. This has to be way taller than anything. So this is like the radius of the Earth, actually. Yeah. So it's like if this is the Earth, then he's as tall as the. Well, he's as tall as the radius of the. There. So there, he's holding the barbell, right? Okay. So there's the radius of the Earth is about 4,000 miles, and he's also about 4,000 miles. So I wanted to see how much work it would be if he lifted the weight now that he's 4,000 miles tall. 4,000 miles, by the way, is approximately 20 million feet. But, so can I use, here's the question now, can I just use the same formula? Right, so then the work, it'll just be, what is it, 1,000 pounds times, this is feet, times 20 million feet? Will this be the work? So I'm asking you a physics question right now. Yeah, Aiden?
We have to integrate the changing gravity because it's so drastic.
Oh, so he's saying, wait, but gravity changes, right? Like, as I was saying before, we have a certain weight on the surface of the Earth, but if we were to go to the moon, we would weigh something different. And certainly, if we were twice as far from the center of the Earth, we would expect to weigh less, right? So that's exactly the point. Is the weight, the barbell, it won't weigh as much when it's 4,000 miles from the surface of the Earth. Anyone know what fraction of its weight it will be? A quarter is correct, yes. So it will actually only weigh, at this point, it will now weigh 250 pounds, which is 1/4 of 1,000. And where did we get that 1/4 factor from? Yeah? The inverse square law is right. So one of the things that Newton put his name on, in addition to most of the things that you guys have learned in this class, is his law of universal gravitation. So this is just FYI. I'm not really going to test you on this formula, but it's relevant to what I'm about to tell you. So it gives a formula for the force between two massive objects. It's the product of their masses divided by the distance between them squared. Of masses m1, m2 at a distance r apart. Okay, I'm not really going to get too much into that, but what I just wanted to point out was the key fact. All I really care about for the purpose of this problem was the 2 right here. The fact that if you made two objects twice as far apart, that factor of 2 would get squared and would actually cut into fourths the force between the object, okay? So if you pulled them, 3 times as far away, then you would only have 1/9 of the attractive force between them. It's a crucial, you have no idea how much of nature was dependent on the fact that this is an inverse square law. It's also super related to electricity and magnetism because charges have the same law of attraction. The force between two charged particles also varies as the inverse square of their distance, which is actually fundamentally related to the research that I'm doing to get my PhD and write my thesis. I'm working with Coulomb attractions all day. But let's examine some of the consequences of that. So using that, I can give you guys a different formula for what the weight of the barbell is going to be that will now vary with the height of the barbell above the surface of the Earth. So the weight, let's say here's the Earth. Let's say this is the radius of the Earth is r, where I told you r was 4,000 miles, or 20 times 10 to the 6th feet. That's the radius of the Earth. And let's say we're at a height, let's say h. So if the barbell is out here, and this is a height h, equals your height above the surface, then your new weight, it's going to be 1,000 times r over r plus h squared. So you can see if you plug in h equals r, which was the situation that I drew over here, then that corresponds to a weight of, well, it'll be 1,000 times r over 2r squared, which is 1,000 times 1/2 squared, which is 250. So this formula gives the right weight, at least according to what we'd already said. Okay, so really, if we want to calculate the work required to lift this barbell, we're going to have to integrate it. We can no longer use the formula over here, F times d, because the force is going to vary with the distance. So here, in fact, let me give you the new formula for work. This formula will become, let me write it like this. It will be the integral of force of x dx for a force that varies with distance. So in this case, it will be the integral of 1,000 times r over r plus h squared. And I was using h. Maybe I should use x. Here, let's call it x instead of h. Here, let's use the letter x. The x, as x goes from 0 up to h. Okay? So I can do this integral really fast. It's 1,000 r squared times -1 over r plus x as x goes from 0 to h. So I get 1,000 r squared. Let's see, that's a 1 over r minus 1 over r plus h. Okay, so I could put in h equals 2r for h equals r, sorry, and see how much work it required to lift the barbell up to this. But that's not actually the point of this whole example. Because I said that the mountain was 4,000 miles tall. Well, why stop there? Well, how about 4 billion miles tall? Or 4 trillion miles tall? You see where I'm going with this? What do I really want to know is how much work would it take to lift this barbell off the surface of the Earth and carry it out to the farthest reaches of the galaxy, basically off to infinity, right? So the next thing that I'm going to do is I'm going to see what happens to this quantity if I let the height go to infinity. Well, in fact, we can see right now, what does this quantity go to if I let the height go off to infinity? This term just goes away as h goes to infinity. And the whole answer I'm left with is 1,000 times r. And what I just did was an example of the next subject of this class, section 7.7. This is a so-called improper integral. This was, what I just did was the integral from 0 to infinity of this quantity. So I will have to pick that up on Friday, and now you see why we're doing it.